Hello and welcome to this lecture. So let me make another important remark. This, what I wrote in the towards the end of last class was I tried to relate. I didn't prove it though. By the way, this requires proof that that this, it's not that difficult, but it requires proof that these three equations hold. And I said that d2 composed with d1 is 0 implies curl composed with grad is 0, and likewise d3 composed with d2 0. Similar calculation shows that this implies divergence composed with curl is 0. Divergence composed with curl is 0. Right. So now the other remark I want to make is that one has an invariant formula for D. Now what does one mean by invariant in this setting? It's, I just mean something which does not use local coordinates as part of the definition. So, and it goes like this. I've already mentioned a special case of this, a formula for D acting on one forms. But in fact, it's true for any K form. So if I start with omega and capital omega Km, so I'll state it as a proposition. Since I already have a definition of D, the claim is that D can be recaptured in this way. D omega acting on x1, x2, xk. So here I'll take x1, x2, xk plus 1 are all vector fields on them. So this, the proposition is that this d omega, whose definition we already know in terms of local coordinates, can be written as minus 1 to the power I minus 1 xi omega x1 xi hat xk plus 1 plus, so this summation is over I, here I less than j between 1 and k plus 1, here between 1 and k plus 1 again, and this time it's minus 1 raised to I plus j omega of the Lie bracket of xi xj x1 xi hat xj hat xk plus 1. Let me explain what these things mean. Well, first of all, when I write a hat over a vector field, it just means that that entry is omitted. So essentially this term omega x1, it's just shorthand for writing omega x1. I go all the way up to xi minus 1, but then I jump to xi plus 1 like this. And similarly this thing, the second term as well, I omit this xi and xj. So That's one thing. The second thing is this, these are xi's are all vector fields, and so when I omega of x1 up to xk plus 1, after I omit xi, I'll get k vector field, so omega will act on that. So this is a function, C infinity function. Omega of x1 up to xk plus 1 is a C infinity function, and I'm just taking the derivation action of the vector field on a function. And well, that's it. There's not much more to say about this, except that there's one interesting thing going on here, which is the following. Note that if I evaluate the whole thing at a point P, this by definition is d omega at P, x1 at P, xk plus 1 at P. And this, of course, the left hand side just depends on x1 at P, xk plus 1 at P. But on the other hand, the right hand side, because of well, two things. One is the Lie bracket term here. Even if I evaluate at P, if I were to evaluate this at P, the way the Lie bracket is defined, it's crucial that these are vector fields, not just tangent vectors, otherwise it doesn't even make sense. So, and moreover, this thing actually depends not just on xi at P and xj at P. It depends on how they are defined in a neighborhood of P. So, and likewise this thing, the first term as well. I am going to take directional derivative along xi of this function. It will matter how this x1, x2, xk plus 1 are defined in a neighborhood of the point. So the upshot is that the left hand side depends only on the values of x1, x2, xk plus 1 at P, but the right hand side seems to depend on the values of xi in a neighborhood of P. But what this formula shows is that in fact, hence the right hand side depends only on omega in a neighborhood of P and x1P, xk plus 1P. So the definition of right hand side, if you are just given x1P, xk plus 1P, the right hand side doesn't even make sense. For instance, the Lie bracket doesn't make sense, neither does this, the first term. So it's essential that we have vector fields rather than individual tangent vectors. But even though we start with vector fields on the right hand side, ultimately what we end up with just depends on tangent vectors at a given point, not on the full vector fields. So, which is not obvious unless, of course, once one has this formula, then it's clear. And this formula is sometimes it's useful. I'll give an example where this can be used, but oftentimes it's more difficult. It's easier to work with local coordinates. So the case k equal to 1 is something that I had mentioned earlier. In that case, d omega acting on x1, x2 would be well, so here I would have to start with, in the first term, I would have to start with I equals 1. So x1 omega x2 minus x2 omega x1, and then here I'll get I plus j, both of them. So here, well, 1 less than or equal to I less than j less than or equal to 2. So there are only two possibilities, I equal to 1, j equals 2 in this. So essentially there's only one term in the sum, and I'll get a negative sign. So omega acting on, and if I omit these two vector fields, there's nothing else remains. So I'm just left with the Lie bracket of x1, x2. This is the formula that I had mentioned earlier. So this is only for one forms. So I want to talk a bit about special classes of classes of K forms, which are especially relevant in topology. So let's make a definition. Omega is said to be closed if d omega is 0. Here 0 of course refers to the 0 form and regarded as a k plus 1 form. And the second thing is omega is exact if omega equals d eta for some eta in omega k minus 1 m. So let's recall this. The two maps which are involved here. The d here refers to two different d's. One is from omega k minus 1 m to omega km, and this d goes from omega k plus 1. So the first condition is that omega is closed if d omega is 0. So in other words, if omega belongs to the kernel of this d here, then omega is said to be closed. And in the second condition, omega is exact if omega is d eta for some eta in omega k minus 1. So in other words, if omega is in the image of this green underlined d, then omega is exact. Let's make some observations about these two conditions, and then I'll give an example. The first thing is that note that if omega is exact, then it is closed, since, well, if omega is exact, omega is d eta, therefore when I take d omega, this is d of d eta, which is 0, since we know that d squared is 0, d composed with d is 0. In fact, let's give this for my next point. I'll give the sum index, right. So dk and dk minus 1. So this IE, so what I've written here, omega is exact, then it's closed amounts to saying that this image of this map dk minus 1 is contained in the kernel of dk. This, so if I have one vector space contained in another, then I can look at the quotient vector space, and that's called the kth de Rham cohomology group. So I'll just put it in brackets since I'm not going to pursue this any further. Let me just say that the kth de Rham cohomology group, in this case it's actually a vector space, and this is HK MR. This is defined to be the kernel of dk modulo this quotient vector space. And the interesting thing is that even though these first of all, this omega k is itself infinite dimensional, and one can check that even this kernel and the image are infinite dimensional subspaces of omega k. But it turns out that if the manifold is compact, for instance, then this quotient space will be finite dimensional. But so let me give an example. Let's take our underlying manifold to be R2 minus 0, the origin, and I'll take the specific one form 1 by x squared plus, rather instead of writing it as 1, I'll write it as minus y this plus x by x squared plus y squared dy. So this is it's a one form on the manifold. Now one can check that d omega in this case is equal to 0. And how does one do that? Well, it's just a matter of dealing with each term. There are two terms here, each one separately. So for instance, the first term, if I write omega as a dx plus b dy, where a and b are functions on M, then d omega is by definition dA wedge dx plus dB wedge dy, and that dA we know what exactly it is. It is del A by del x dx plus del A by del y dy wedge dx plus, and dB is del B by del x dx plus del B by del y dy wedge dy. And so in the first expression here, this dx, I have a dx here, and dx wedge dx will be 0. So I'll just get one term dy corresponding to dy wedge dx. Similarly here I'll get dx wedge dy. So let's write those two terms, del A by del y dy wedge dx plus del b by del x dx wedge dy, and I can swap this dx wedge dy wedge dx is minus dx wedge dy. So I can, after doing that and combining, I'll get del b by del x minus del a by del y dx wedge dy. So this is a general formula valid on any manifold. If I take D of one form, of course on a manifold, like I don't have this dx and dy defined on the whole manifold. In a chart, I can do this computation. And to say that d omega is 0, therefore d omega is 0 if and only if del b by del x equal to del a by del y. So in this case, so going back to this example that we have here, so all I have to do is I have to compute the, so this is b and the first thing is a. So I have to compute the partial derivative of this with respect to x and this with respect to y and check that they are equal. And in fact, so they will, so right, okay. So in our case, b is the function. So let me just do this one example. So b is the function x by x squared plus y squared. A is the function minus y by x squared plus y squared. And if I take del b by del x, I'll end up getting, well, to do a bit of calculation here. So this is use the quotient rule. So x squared plus y squared times the partial derivative of this minus x times the partial derivative 2x x squared plus y squared whole thing squared. Well, that's what I'll, so y squared minus x squared divided by x squared plus y squared squared. And if I do it for this, del a by del y will be similar. So x squared plus y squared, here I'll get a minus 1 minus, so plus, it becomes plus 2y, and then x squared plus y squared whole thing squared. So 2y squared minus, again I'll get the same thing, y squared minus x squared divided by x squared plus y squared. So this form is closed. I claim that it's not exact, omega is not exact. If it is, then there exists a C infinity function on R2 minus 0 such that with omega equal to df. So, and let's see why this gives a, quickly see why this gives a contradiction. So I look at this circle, the unit circle. Let sigma from 0 to pi to R2 minus 0 be sigma t is cos t sin t. Now I'll compose this f and sigma. F composed with sigma, so f is a map on this and sigma is a map from here to here. So f is to r, and this is from 0 to pi. So I'll get 0 to pi to r. So I get a map. And what we need about this map is, well, two things. One is f composed with sigma 0. Sigma 0 is f of 1, 0. And f composed with sigma 2 pi is the same thing, f of 1, 0. So, but on the other hand, yeah, so this is, I've not yet used this condition, omega equal to df. So let's do that now. So let's compute the derivative of f composed with sigma. D by dt of f composed with sigma is, by the chain rule, df of sigma prime t, where here of course df is I'm using the derivative interpretation of df, which is the same thing as the one form df, and this is omega, since I've assumed df is omega, so this is omega of sigma prime t. So omega at sigma t, at the point sigma t. Now sigma t is a point on the circle. So if I look at the formula for omega, this x squared plus y squared becomes 1 on the circle. So I'll just get minus y dx plus x dy, which is, the y coordinate is sine t minus sine t dx plus cos t dy, and this thing evaluated on sigma prime, which is, well, it is sigma is cos, so minus sine t cos t. It's better that I write it as a tangent, use the tangent vector notation, then we'll see it's even more clear. So minus sine t del by del x plus cos t del by del y. Now, so I'll get 4 terms, but the point is these are dual one forms. So dx acting on del by del y will be 0, etc. So I'll just end up getting this, and this will combine to give me sine squared, and this will combine to give me cos squared. So sine squared t plus cos squared t. And therefore, which is 1, i.e. f composed with sigma is strictly increasing on 0, 1, which will imply that f composed with sigma 0 is strictly less than f composed with sigma 1, which is a contradiction, because we saw that these, oh sorry, not 1, it is 2 pi. So 2 pi. We saw that these two values are the same, so this equal to this. So therefore this form is not exact. So let's stop here and resume with the discussion of orientation and in terms of and the connection with differential forms and manifolds. Okay, thank you.